Hi, my name is Jeff Edmonds, and this is an introduction to 8051 assembly. Here's some information on where to download the simulator. So this line shows the syntax of the move operation. As you can see, the source follows the destination. For example, in this line, the value 5 is assigned to register 0. Values are preceded by the pound symbol. To move from one register to another, you must first move it to the accumulator. Here, the value in register 0 is first moved to the accumulator, and from there it's moved to register 1. When a number is not preceded by the pound sign, it refers to an address in RAM. In this line, the address 32 could also be written in hexadecimal as 20 followed by an H. Values can also be assigned in hexadecimal. When preceding a register by the @ symbol, it takes the value stored in that register as a memory address. For instance, this line places the value 64 into register 0, and the following line places the value 5 into memory address 64. The accumulator is a specialized register that is used for arithmetic operations and logic. This first line assigns the value 2 to the accumulator, and the next line adds the value 3 to the value that was previously placed in the accumulator. So the new value in the accumulator would therefore be the number 5. The add C instruction is like the add instruction, except that it also includes the carry flag and the addition. In this line, 255 is placed in the accumulator. 1 is added to 255, setting the carry flag to 1. This leaves 0 in the accumulator. Then, using the add C instruction, the value 1 and the 1 that is left in the carry flag are both added together, so that there is a value of 2 left in the accumulator. If the add instruction had been used instead, the value in the accumulator would be 1. When using the sub instruction, the carry flag is always used. In this example, since the carry flag was already set, the result would be 3. If the carry flag was not already set, the end value would have been 4. The increment and decrement instructions work like the ++ or - in Java or a similar language. Increment and decrement. Multiplication and division can also be done. To do so, you must first place the multiplier or the divisor in the specialized B register. This operation multiplies the accumulator with B, and this operation, this is the multiply, and this operation divides the value in the accumulator by the value in B. The respective results are stored in the accumulator. The overflow flag will be set if the result is too large or if the denominator was 0. The B register will also hold any remainder from the division operation. Labels and jumps work together. The jump instruction tells the program counter to move to start executing from the labeled section of code. Here's the jump instruction. In this example, the value 1 is assigned to the accumulator. The value 2 is assigned to register 0. Then the jump instruction skips to the section of code labeled "This is a label." Here's the jump instruction, and here is the label. You can tell it's the label because it's followed by a colon. So the last operation adds 2 to 1, resulting in 3. Note that the operation where the value 3 is moved to register 0 is skipped. Also note that the tab under the label is added for readability. And it does not contribute to the syntax. Jump 0 and jump not 0 can both be used in place of jump. Here's jump not 0, and here's jump 0. These are conditionals where the operation is followed if and only if the result is 0 or not 0, respectively. JC and JNC are similar, but rely on if or if not the carry flag has been set. The register banks allow the general purpose registers to access more RAM. By default, they are set to use the first 8 bytes of RAM. But with the set bank and clear instructions, they can also use the second, third, or fourth set of 8 bytes. This example changes to the third set of register banks. You can refer to the instruction set to see other settings. .8051 RAM uses a first in, first out stack data structure. The stack pointer position is always 1 less than the current position of the stack. The stack can be changed with the push and pop instructions. In this code segment, number 5 is placed into memory address 0. It's then pushed onto the stack. Then the number 8 is assigned to address 0. When the pop operation is applied to memory 0, it removes the value 8 and retrieves the value 5 from the stack, putting it back into memory address 0. Subroutine calls are similar to jumps. The difference is that the call instruction pushes the program counter address of the next instruction after the call onto the stack so that it can return there after it runs the subroutine. In this example, we first jump to the start label. The value 7 is assigned to register 3. Then the all of the zeros subroutine is called. So first we'll move to this page to see that the all the zeros call has been called. Here's the all the zeros label and therefore the all the zeros subroutine. So this subroutine simply clears all 8 registers. After the 7th register is cleared, the return statement pops the program counter address off the stack and returns to the instruction immediately after the call. Then the value 4 is placed in the register 7. And then the subroutine is called once again. It's always suggested that you push values of registers onto the stack before making a subroutine call, because the call can change the values in the register. So that concludes the introduction to 8051 assembly. I recommend reading through the manual and doing the practice exercises to get a better understanding of 8051 assembly, especially in regards to memory management. I think that's where assembly kind of gets tricky, at least in my opinion. And in the next video, we will work directly with the 8051 simulator. All right, thanks a lot.